In this video, we're going to discuss a little about abelian groups. Alright, but before that, let me introduce a notation. If star is a binary operation on G, then x star x is denoted by x squared. Alright, this is the notation we're going to use throughout this video. Well, for one characterization. Okay, let's define an abelian group. A group G star, where G is the underlying set and star is the binary operation on G, this algebraic structure is said to be an abelian group. Is said to be abelian, or it's also called commutative. Commutative group. Commutative group if we have for all x, y belonging to G the condition x star y equals y star x. This is the commutative property for star if the commutative property holds. Now, if you remember, commutative property is not a necessary condition for G star, the algebraic structure G star, to form a group. But to form an abelian group, it's necessary. Not every group is an abelian group. Alright, we'll discuss the examples, plenty of examples in later videos. Let's just stick to abelian groups right now. Now this is the definition. Okay, this is the definition. Now I'm going to state and prove a theorem which will characterize an abelian group. Okay, G star is an abelian group. First of all, consider G star to be a group. Let G star be a group. Then G star is an abelian group if and only if for all x, y belonging to G, what was the condition? Right, x star y squared is equal to x squared y squared. X squared y squared. Alright, this is one of the characterizations of abelian groups. Now to prove it, now consider this G star to be a group, this algebraic structure G star to be a group. Now let's prove this part first, forward implication. For this, let G star be an abelian group. Okay, we're going to assume that G star is an abelian group. Then we should show that, or prove that, for all x, y belonging to G, x star y whole squared is equal to x squared y squared. Alright, now this means okay, in order to prove this statement, we're going to consider two arbitrary elements. For this, let x, y belonging to G be arbitrary. Okay, arbitrary. Then x star y squared is equal to, according to this notation, we're giving this thing, so we can write this thing, x star y star x star y Alright, now this means, now since star is associative, we can remove the parenthesis as we want, and we can insert the parenthesis as we want, covering as many elements as we want. Okay, so first of all, let me write it like this by removing the parenthesis. Then let me reintroduce the parenthesis in the middle part and write it like this. Now since G star is an abelian group, we can write this as x star y, okay, which means we have x star y star y. Now we can again reintroduce the parenthesis like this, which shall give us, this will give us x squared, and this will give us y squared. Okay, so the forward implication has been proved. Now let's prove the backward implication. For this part, let the statement for all xy in G x star y squared x squared y squared be true. Okay, let this statement be true. Then we should show that G star is abelian. Okay, we should show that G star is an abelian group, which means, as per the definition, we should show that for all AB belonging to G, what should we have? A star B star B star A. We need to prove this thing. Okay, we need to prove this thing in order to prove that G star is abelian. Okay, now for this, what are we going to do? We're going to take, let AB belonging to G be arbitrary. Alright, be arbitrary. Then what is going to happen? As per the given condition, A star B whole squared will be equal to A squared star B squared, because A and B are elements of G, so this condition should hold. Okay, now let's see. This should imply A star B star A star B to be equal to A star B star B. I'm removing the parenthesis right now. I've removed the parenthesis already. Okay, now let's see. We can operate the left side of this equation by A inverse and proceed like this. So if we insert the parentheses like this, we're going to get this to be the identity element. So E star B is simply B, and the remaining A star B is as it is. Again, if we introduce the parenthesis like this, this will be the identity E, and E star A means A star B star B. Okay, now let's introduce the inverse of B over here, like this, and since these two are identities, these two give the identities, we can say that A star B will be equal to B star A. So since A and B were arbitrary, the proof for the backward implication is also complete. So on the whole, this characterization holds. Okay, that's all about this characterization. Now let me just discuss one more problem. This is not a characterization but a problem. Okay, quite a basic problem but an interesting one. Let's call it uh, just a question. Mm, let G star be a group. Let G star be a group. Okay, we're given a group. Let every element of G be its own inverse. Own inverse. Then prove that G star is an abelian group. Okay, you can find this problem on almost every textbook out there. Okay, some of them state and prove it as a theorem, but most of the textbooks include this as an exercise. Okay, now let's just be a little bit lazy and write let the given conditions hold. Let the given conditions hold. Okay, then for all x belonging to G, the element is its own inverse. So we can write something like this, where E is the identity of the given group. Identity of the given group. Alright. Now we should show that G star is an abelian group. Okay, G star is an abelian group. And then that is, what should we show? That is, we should show that for all AB belonging to G, as per the definition of the abelian group, A star B is equal to B star A. Alright? For this, let AB belonging to G be arbitrary. Alright? Since we need to prove the statement for general elements A and B, let A and B belonging to G be arbitrary. Then let's start with the left hand side. Let's write A star B as A star B star the identity element. Okay, identity element. So A star B is as it is. Now since G is a group, A star B should be in G as well as B star A should be in G. Since these two elements are in G, in particular since B star A is in G, B star A should satisfy this condition, this given condition. So what we can do is we can replace E with B star A star B star A. Okay, now we can write it as A star B star B star A star B star A. Okay, now let's see A star B. Now if we introduce the parenthesis over here, this will be the identity element, since B is an element of G. So this equation will imply this to be an identity, which reduces this to A star B star A. Okay, and if we introduce the parenthesis over here, this will be the identity element, so we can remove it and write it as B star A. So for any two elements A and B of G, we've obtained A star B to be equal to B star A. So this holds, and therefore G star is an abelian group. Okay, abelian group. Now I'm gonna stop this video right now. Okay, this is all that we're gonna discuss about abelian groups for the time being. We're going to discuss a little bit more about abelian groups in the subsequent videos, but for now let's just uh, be satisfied with the all right, this small introduction to abelian group. Okay, and in the next video I'll be discussing about the subgroups, what we mean by a subgroup, and some characterizations for a subgroup. Okay, and in the video after the video on subgroups, I'm going to discuss about integral powers of an element of a group, and then we're going to talk about a lot of different topics related to group theory. Alright, okay, that's it for today. Thank you very much.